Hi, good evening, everyone. So right now we're probably at the point where you've finished your chapter already, and then you realize that, there's so many things to understand and learn from this chapter. Even if you look at this final page you have at the back of the chapter, there's I know I'm talking about energy, then there's this formula, there's another formula, there's other formulas here, right? Then how come there's a change of state, change of matter, all these different things? There's so many different questions, right? Like for this part over here, there's a whole question whereby how come at this temperature, even though energy is being transferred into it, how come there's no change of temperature? Like those kind of things. But we're not talking about those questions right now. The main questions that we have so far that confuses us are the questions whereby let's, uh, let's draw it down. Okay, let's say I have I have like a that okay I have this container and it's full of water, right? And let's say the water it's 24 degrees Celsius. You know what, I'm just going to look for, I'm going to pause, I'm going to look at a textbook, I'm going to find a question. Okay, I went away for a while, but the pause looks like it didn't go away. Anyway, so on page number 173, the question that I have over here, perfect, 24 degrees or so. Yes, it talks about I have a steel spoon, right? This steel spoon is, it's very, very hot. How hot is it? It's 150 degrees Celsius, right? Let me not care about the mass first. That's not the point I want to talk about now. And we have this thing. It goes bloop, goes inside here. And the question is, what happens? What's the final temperature of the water? These kind of questions. All right. I'd like to put into place these ideas of how do I figure out a way to write the equation? What do I do? Right? So I'm going to put these two things for you. I'd like you to first consider energy transfer. I realize I'm losing the time. I should pause and just write everything out. Give me a moment. Ta-da, magic. Okay, so when we talk about where's the energy transferred, is it transferred in or out? Right? And once you figure out that if something is hotter, it's going to transfer to the cooler one, that's definitely going to be energy out, right? And if I'm the one with the lower temperature, and I'm going to be in contact with something with a higher temperature, energy will transfer in, right? So that helps in writing the equation and figuring out, because that's the first thing we need to understand. So now between these two things, right, which one will experience energy out, transfer out? So this is this one, right? Because it's a high temperature. This is where energy will transfer in. Energy will be transferred out of the spoon, energy will be transferred in to the water. Now this helps with understanding whether or not how do I do the theta minus the temperature change, right? That's one of the questions that you're asking me. If that sounds weird, don't worry, we'll get to the example and we'll show you how it works. All right. So first thing is about understanding what's happening. Is the energy transfer in or out, right? Now the second thing to ask yourself, right, is what changed in this whole process? Was there a change of temperature or was there a change of state? Now, why this is an important question to ask yourself is because that tells you what formula I'll be using. And I'm pretty sure by now you know that when it comes to temperature, the formulas that we'll talk about in terms of the energy transfer, right? This one would be mc theta, and over here for change of state it will be ml, right? Where C over here, let's get my highlighter thingy, right? This is my specific heat capacity of a certain substance, and this L over here, well, it depends. It could be specific latent heat of fusion or specific latent heat of vaporization of a substance. Okay, so just need to ask yourself this question. Let's show you how the working actually looks like once you've asked yourself these questions. Okay, so again, this is page number 173. It's a work example, but hopefully this helps you get some clarity. Okay, now there's more detail. Let me just write down the detail inside here. I'm going to pause and write the details for you because time is important for everybody. Okay, pause. Okay, so these are all the extra details you need to know. So this steel spoon originally 150 degrees Celsius, and the mass is 0.025 kg or 25 grams. It is told to me that the specific heat capacity of steel, which is a spoon, is 460 joules per kg degrees Celsius. Now this over here, sorry, excuse me. this is over here is 24 degrees Celsius. The mass is 300 grams or 0.3 kg, and the specific capacity of water is this. Now, let's start with our equation. It's always going to be whatever energy transferred out of something, especially now in this interaction, right? Whatever the energy was transferred out will be the energy transferred in to the other thing. Where was energy transferred out of? It was transferred out of the spoon, right? And that energy will be equal to the energy that's transferred into the water, So let's write it this way, okay? So doesn't matter how I write it. I'm going to pause. Yeah, I'm going to pause. Oh wait, no pause. I'm supposed to say one thing. The question is asking for, how can I forget that? What's the question asking for? The question is asking for what is the final temperature when this spoon goes inside here and I want to transfer energy, right? What's the final temperature then? Right? So we're gonna say what's the final temperature? Let the final temperature, right? Let's say the final temperature, right, is theta F for final. Okay, so how are we going to write it out? Let's start first with this energy in equals to that energy out. Fantastic. So this one over here, because it's a change of temperature, I'm going to be using my MC change in theta, right? Of course, because I'm talking about water here, this M will be the mass of my water. This C will be my specific capacity of my water. On the other side, excuse me, so sorry. Over here is going to be my mass, my spoon, my specific capacity of my spoon, and this is going to be a change of temperature of my spoon. Sorry. Now, I could edit it, but I'm just going to move on. So, of course, here, right, here is the struggle over here, right? What is this change of temperature going to be? And how do I understand it? Okay, so let me show the answer, and then let's try to make sense of it. Now, as you have seen in many of the workings we did in class, this is how it looks like. But I think there's some confusion of like, this one is the final temperature, this initial temperature. This one is the initial temperature, this is the final temperature. Why like that? Huh? How come? All right, so let's try to use an analogy, okay? So take a look at this. Okay, let's say this over here is John. Okay, now at first in the morning he had $2, but at the end of the day, wow, he has $10. Right? So they ask you, how much do you gain? How much came into your pocket? You go, how much came in? Oh, 10 minus 2. That's how much came in, right? And it makes sense, right? You can take the bigger and this is smaller, right? In this case, right? Now let's now look at this person over here. This person, let's say this person is James. Okay. Now at the start of the day, he had, let's say, $25. Right? At the end of the day, he got only $7. I ask you, how much got out? How much went out? How much went out? How much went out? What I say, 7 minus 25, or what I say, how much went out? Oh, 25 minus 7. I'll go 25 minus 7, this is how much went out, isn't it? Right? So maybe one way to help you all to see how to do it, right? If I'm talking about the into, right, it will make sense if I'm going to go with the bigger and the smaller, correct? Which is in this case, this minus this, right? And then when I was talking about how much went out, how much you lose, this one over here, right? It will make sense to go with the big amount and then the small amount, because that's what makes sense, right? In terms of the out, right? Hopefully, if you can understand this analogy, it makes more sense on how to write this part, which seems to be a struggle for many of you. So perhaps looking at this part over here helps you to figure out how to write this over here. Now, if this is fine, it makes it, well, that's half the better one, because in this question, right, there was only a change of temperature, not a change of state. All right, so I'm not going to finish up this question over here. The focus for this part was to figure out how do I write this inside here and how do I even start in the first place. Okay, the rest of the workings, you can find it once again on page number 173 of the textbook. It is a work example. Basically, I'm just trying to find what is this over here. Okay, so let's now do a question where I'm not just looking at a change of temperature, but there's also a change of state. Okay, so let me make this screen a little, what just happened? Nope. Like that, yes. Okay, I'm going to move it a little bit and let's go to another question where there's a change of state too. Okay, I'm taking the question from page number 185, question number 2 of section B, the structured questions. So allow me to just draw out the question. Okay, it tells us that I have a paper cup. Okay, and this paper cup, let's say the cup looks like this. This paper cup contains 200 grams of water, and this water is at 30 degrees Celsius. Now, what do I know? What else do I know? It tells me that I have some ice cubes which are going to be added into the water, right? How many grams of ice cubes? Well, I have 40 grams of ice cubes, right? And these ice cubes are at negative 10 degrees Celsius. I'm going to add them into the water, right? The question does say also, right, that we assume that all the energy transfers is only between the ice and the water. That means there's no energy loss anywhere else. Don't think about conduction, convection, radiation. No, just whatever energy is just between here and here. Okay, what will the final temperature be? Okay, let's also put the point over here that in this question, how come this one gram, this one gram, how come just not kg? How come so far? Well, it's because in this question, they actually gave us the specific capacity of ice, water, latent heat, everything in grams. So let's be clear. Okay, I'm going to pause and write down on the side all the information that is needed for this question. I'm not pausing. Pause. Okay, so what's given? The specific heat capacity of ice is this much. The specific heat capacity of water is this much. And the specific latent heat of fusion of water, right, is this much. That means when I go from ice to liquid, right? If it was going to be liquid to gas, there will be specific latent heat of vaporization of water. Okay, this is fusion because I'm going from the solid to liquid. Right, these are all I need for this question. So let's go back to this up here. Right, so I'm going to ask myself, which energy transferred, which one's in, which one's out, which one had energy into it, which one had energy out of it. No, why am I moving that way? Excuse me. Right, so yes, much better. Okay, so when you look at this over here, right, which one would have energy going out? Which have energy coming in? Clearly, this over here is the one which is hotter. This is colder, right? So energy will be out, transferred out of this 30 degrees Celsius water into the ice cube. So this will receive energy, correct? Energy in, energy transferred into the ice cube. So I have this part over here, which makes it a bit easier for myself. I'm going to write out energy. Why is my thing go so far in? Energy transfer. I should pause it. Give me a moment. Okay, there you go. Energy transferred into the ice cube will be equal to energy transferred out of the water and cup. However, this is something that's incomplete because we know that the ice cube does not remain as an ice cube, correct? Now we know this ice cube is going to change from. Let's see what's it change into. Let's figure it out. Okay, the ice cube over here, it is initially negative 10 degrees, correct? Wait a minute. What's the final temperature? Ooh, let's do the same thing. Okay, let this be the final temperature. Okay, because I know that this over here, the 30 degrees Celsius, right? The water over here, and this is the paper cup, is going to drop from 30 degrees Celsius to this temperature over here, correct? But the ice cube over here, which is initially negative 10 degrees Celsius, is going to change temperature, change state, and change temperature to this temperature over here. Not sure what I meant? That's what I meant. I'm first at a negative 10 degrees Celsius ice cube. It is going to change in temperature to 0 degrees Celsius, right? This was a change in temperature. Change in temperature. Now, once I hit 0 degrees Celsius, which is my melting point, what comes next? I'm going to change from ice to liquid. That is 0 degrees Celsius. This is a change of state. Now, once the state has been changed and it's 0 degrees Celsius, then I will increase my temperature to that of this final temperature. And once again, this is a change of temperature. Where am I? What am I doing? I'm asking myself this question over here. What change? Change of state or change of temperature? If there was a change of temperature, then I would need to use this formula over here. If there's a change of state, I have to use this formula over here. Let's go back down and let's give it a try. Okay, so energy transfer to the ice cube. I know that it's going to go through all these things over here. Okay, so let's do the easier one. Let's do the one on the right side. Why is it not so big? That's so weird. Okay, let's look at the one on the right side over here. Okay, energy transferred out of the cup, of the water in the cup. Okay, let's see if we can do that. M of the cup, of the water, the mass of the water in the cup. C, which is my specific capacity of water, and change of temperature. Okay, remember this is out. That's the loss, correct? So if I'm going to ask you, what's the loss? I'm going to say, oh, the big amount of money I used to have and minus my final amount, which I have, correct? Okay, if not sure, go back up to this example over here, correct? What would James say? James would say, oh, out, how much money out? 25 minus 7 now, right? So it's not so much of the initial minus final minus initial, right? It is more of making sense of the question. If this was out, how much you lost, I'll take this minus that, right? If it's how much you gain, how much in, I'll take this minus that. That number would make sense. Okay, back here again, don't shift anything. So in this case over here, I used to be 30 degrees Celsius, correct? Why is it not so thin now? I'm just okay, and then I'll get this, correct? Why is the brush size so different? Okay, but this should make sense to you because that is out. What went out of it? How much do I lose? Right? That's why 30 minus theta f. Now let's work on the side over here. Okay, remember that we need to take note of 1, 2, 3. Okay, there seems to be 4 things, but it's just really 1, then 2, then 3. Okay, so that means I'll have 3 different formulas. So let's work that out. Okay, so when I go from negative 10 degrees Celsius to 0 degrees Celsius as an ice cube, it'll be M, mass of the ice cube, specific capacity of ice cube. The change of temperature would be, what would it be? I was this, now I'm this, correct? That's again, correct? So I'm going to take the final minus this one. So it's going to be 0 degrees minus 10. Right? Again, look at the previous example if you're not sure. Plus, now this part over here. This is a change of state, correct? So just we go M, L, continuum fusion. Then over here, I change from liquid to liquid to change the temperature. This was my initial temperature. This is my final temperature. How much was transferred in? How much did I gain? So therefore, this would be M, C. Well, this C will be a bit different, correct? This was when ice. So let me put ice over here. This would be water, correct? And my theta in this case would be theta F minus 0 degrees Celsius. That was a gain. That was how much went into the ice cube. All right? So when we put together everything and we substitute all of the things we have up there, it should look something like this. The mass of the ice cube, so remind yourself, where's the mass of the ice cube? It's here, 40 grams, right? Is that 200 grams or 40 grams? I wrote ice cube over here, so all the mass over here would be that of the ice cube. It won't be the same as this over here. This is water of the cup. So let's try. Ready? Mass of the ice cube, 40. Why is it so thick now? Why is it not? Okay, that's one point. Multiplied by, what is C? C of the ice. This is going to be 2.1. Multiplied by 0 minus 10, that's 10. plus, again, mass of the ice, so that's 40 grams, 40 multiplied by specific heat of fusion, that is going to be, well, this one up here, correct? So that's 334. I hope you don't mind that I'm actually writing on a video, not pausing it. I hope this helps you a little bit more. Now, finally, this M over here, is it 40 or 200? Look here, I'm talking about my ice cube, so it has to be this 40 over here. See, that's also something very important for you to remember. Writing out my statement really saves myself all that trouble. This one is water. Which one? Which one is it? See, yes, it's this mass over here. But once it turns to water, I will still use the same one, which I'll use on the side over here, right? This over here would be 4.2 multiplied by, where did the 0 go? Well, theta f minus 0 is just theta f. On this side over here, what's it become? Okay, remember it's an equation, so I'm doing the left-hand side first, now the right-hand side. This is the mass of the water in cup, so that's going to be 200 grams. 200 C. Is it CI or CF? Oh no, CI or CW. It's water, isn't it? So as we CW, this over here, 4.2. 4.2. In this case, a change of temperature would be, again, 30 minus theta f. Now, the rest of this over here, which I'm not going to continue doing, that's mathematics. That's about you expanding it and trying to find my unknown, which is theta f. That's not the important part of this exercise of this 20-minute video, 23-minute video. All right? Now, what's the point of this video once again? Let's remember that we're trying to understand how to do the questions. And it really just comes down to you understanding two questions. Is energy transfer in or is energy transfer out? And then you ask yourself, in those cases where energy transfer in and out, what changed? Was it a change of temperature or a change of state? It helps a lot if you draw it out this way to figure out what was the change, right? Okay, that's really a 23-minute video. I really hope this helps. If there's any other questions, please let me know. Do try the different questions inside your textbook. If you need to, I can give you the answers, but generally, this is the basic question guide for the questions of thermal properties of matter. There you go. All the best.